Hello. Well, hopefully third time's a charm. Third time making this video. The first time the computer crashed. The second time I accidentally deleted it when I was done. And here we go again. Alright, well, in the prior video we looked at the quotient rule. And I know I said we were going to move on to the chain rule, but I wanted to do a few more examples with you. Okay, so here's your quotient rule. I've also written down a couple of derivatives that we know, and we found the derivative of sine by using the definition of our derivative and that limit process. And that's a painful way to find a derivative, but it does work. And that's how we found the derivative of sine to be cosine. And that is just an amazing thing to me, that the cosine function describes the slope of the sine function at any point x. That's a cool thing. Likewise, the negation of the sine function describes the slope of the cosine function. Another amazing thing. Okay, well, what about some of the other trig functions? What about something like tangent? Well, if we want to find the derivative of the tangent, there's, where do you start? Do you use the limit process? Well, you could try that, but I certainly don't want to if I don't have to. So I'm going to recognize that I can actually rewrite, tangent as the sine over the cosine. It's the same thing. That is what tangent is by definition. Okay, so now it looks like I have a quotient, and it's in terms of some functions that I already know the derivative of, so I can go ahead and apply the quotient rule to it. So let's go ahead and do that. The derivative of y with respect to x. Again, I'm partial to this notation because it really drives home the fact that we're finding a slope, or at least an expression that describes the slope at a particular point. Okay, let's apply the quotient rule. It says take your denominator, which in this case is just cosine, and multiply it by the derivative of the numerator. Well, what's the derivative of sine? And we know that that is cosine. And then it tells us to subtract from it the numerator multiplied by the derivative of the denominator. And the derivative of cosine is negative sine. I'm actually going to use some parentheses here just to make sure you don't think that we're subtracting these. Okay, so this is all going to be divided by the denominator squared. Okay, and I know in prior examples I said, well, once you find your derivative, you're done. Once the calculus is done, you're done, and that's true even in this case. But if we simplify it, it'll be fairly rewarding in the end. This is one of those times where we actually want to take the time to simplify. Okay, up top we have cosine squared. And negative sine of x times the negative sine of x is actually positive sine of x. Positive sine squared of x, sorry. All divided by cosine squared. Okay, so I hope at this point, I hope you don't have a disease which I call cancel crazy. Some people look at something like this and they see a cosine squared up here and a cosine squared down here and they want to start canceling. And the only problem with that is we have addition right here. If this were multiplication, we could reduce those, but it's not, so we have to do something else. Well, it turns out the numerator should look familiar to you. It should look familiar from a trig book, from a pre-calc class, or maybe you've been perusing the back cover of your calculus book and you notice this identity that said the cosine squared plus the sine squared equals 1. And this is our Pythagorean identity. Very easy identity to illustrate graphically, by the way. We won't do that right now, but here you go. 1 over cosine squared looks like the derivative, and I can actually simplify that. I don't know if it's simpler, but, well, yeah, it's simpler, to secant squared. Another fascinating result. The derivative of tangent is the secant square. I don't know if you understand what that really means. That, tangent does, see if I can do this real quick. Tangent does something like this, doesn't it? Okay? and then you have these asymptotes at, I think that's pi over 2, and I think this is negative pi over 2, and then it does that some more out here, and it just kind of does this forever and ever in both directions. Well, what is this saying? This says that this secant curve right here, if I wanted to know the slope of the tangent line right here at pi over 4, here's pi over 4 right here. If I wanted to know what is the slope of that tangent line, well, I would take pi over 4 and I would plug it into secant, take the secant of pi over 4 and square it, and that would be the slope of that tangent line. That's a pretty cool thing to me. And that will work at whatever point you want to pick. Okay, let's look at one more example, and let's look at one of the reciprocal functions. How about cosecant? I'll use function notation this time, just to mix it up a little bit. Whoops, cosecant of x. Okay, well, I'm certainly not going to use the limit process on this, but I'm going to do the same thing that I did in the prior example, which is rewrite it in terms of a function that I know its derivative of, and I know sine's derivative. These are the same things. So now let's go ahead and find the derivative of cosecant by using the quotient rule. Quotient rule says take the denominator and multiply it by the derivative of the numerator. What's the derivative of 1? Hopefully everybody said 0. And we subtract from it the numerator, which is 1, times the derivative of the denominator. What's the derivative of sine? Hopefully you said cosine. Okay, and this is all over the denominator squared. Okay, so now, like before, this doesn't take much to simplify. This is just 0, so we're left with negative cosine x up top, and down below I have a sine squared. And you might be tempted to leave it like that, and technically this is the derivative, but we could go a little bit further by noticing that we can actually break up our denominator into sine times sine. Oops, times 1 over the sine of x. Okay, this is the same thing, I just broke it up. And now you'll recognize this as cotangent. And you recognize this as cosecant. So it's not as neat of a result. It's still a cool result. It's still a cool result. It's not as tight or tidy as this being a derivative. That's just nice and neat. Or even cosine being the derivative of sine. So there you go. You can find the reciprocal trig function derivatives by using the quotient rule, and you can find tangent as well using the quotient rule. Okay, so there you have it. I promise you in the next video we will tackle the chain rule. See you around.